So the next half of this lecture is going to get into a special kind of tree known as a rooted tree. So what a rooted tree is it's just a tree with a distinguished vertex. So just a vertex that we pick on the tree and we say, this is a special vertex. It's the vertex that we're going to call the root. For every vertex in the graph, the level of a vertex is just the length of the path. So I say the here because we've just characterized that trees are the graphs for which there's a unique path between any pairs of vertices. So here the word the means that there's just one path and this is it. So we say the level of a vertex is the length of the path from that vertex to the root. There's only one path, it's just however long it is, that's the level of the vertex. And then we just note that the root is the unique vertex at level 0. So as an example, let's draw a tree, a rooted tree in this case. So this one I'm going to draw with root 1. We'll just label them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are our vertex labels. This is what we're calling the root. That was the one we've distinguished for this particular tree. And then for any other vertex, there's a unique path back up to the root. So for example, this vertex 6, there's a unique path that goes to the root. For the vertex 9, there's a unique path that goes to the vertex, which is the root. And so we can lay out our tree in this way, and we can see that the way I've positioned my vertices is I put them at levels. So maybe we'll indicate that this one is level 0. And then 2 and 3, these are level 1 because there is a path of length 1 taking them back to the root. These ones here, these are at level 2. And these ones down here, these are at level 3. If my graph wasn't laid out in this way, we could still figure out what the level of a vertex is. For example, 12. I just go back along the path to the root. So 1, 2, 3. There's 3 edges that I have to travel to get back to the root, so it's a path of length 3, and that's why it's level 3. So this is an example of a rooted tree where 1 is the root, and we've laid everything else coming downwards based on their levels. So here's a bit more terminology. The height of a rooted tree is just the maximum level of a vertex. So in our previous example, this is what we'd call a height 3 tree, or a height 3 rooted tree. Every non-root vertex v at level I is adjacent to exactly one vertex u at level I minus 1. We call u the parent of v, and we say v is the child of u. So for example, if I look at this vertex 5 and vertex 18, we say 5 is the parent of 18, and we also say that 18 is a child of 5. Notice the use of these words. 5 is the parent. There's only one parent to 18 in a rooted tree. It's the vertex in the level right above it that's adjacent to it. As opposed to a child, there could be more than one child. So 18 is a child of 5. 11 is also a child of 5. For every vertex v, there is a walk up the tree to the root obtained by moving to the parent vertex at each step. So for example, if I'm down here at 6, I could go up the tree, go to its parent 18, then go to the parent of 18, which is 5, then the parent of 5, which is back to the root 3. Every vertex along this path that goes up to the root is called an ancestor to 6. So let's indicate this walk up from 6. So what we have is that 18, 5, and 3 are ancestors of 6. Note that 11 is not an ancestor of 6. And again, the reason is even though 11 is seemingly sitting above 6 in sort of this subtree that's sitting here, it's not on the path that takes 6 back up to the root 3. So we also say, in terms of ancestors, we also have descendants. So 6 is a descendant of 18. 6 is a descendant of 18. It's also a descendant of 5, and it's also a descendant of 3. So you can see the relationship between ancestors and descendants. So that's just a little bit of terminology that we have for rooted trees. Now we are also going to be interested in subtrees. So for example, if I'm looking at this big tree and then I'm just interested in this part of the tree. So starting at 5, everything below it, so all its descendants. Then this is a subtree of the big tree T, but it's rooted at 5. So what we can do is we can say, consider the subtree rooted at 5. But then we could also be interested in the subtree of that, which is rooted at 18. So this is basically what our definition above is saying. So if V is a vertex of a rooted tree at a certain level, so here we've got 5 is at level 1, then we define T prime to be the subgraph of T induced by V together with its descendants. So we take 5, all of its descendants, and form the induced subtree of that. And that's the subtree rooted at 5. And similarly for the subtree rooted at 18. Now next, we can talk about isomorphisms of rooted trees. So if T1 and T2 are rooted trees, we say that T1 and T2 are isomorphic as rooted trees if there exists a bijection between their vertex sets, satisfying the fact that if there is an edge from U to V in T1, then there is a corresponding edge from F of U to F of V in E2. So that's just graph isomorphism. That's all this first part is. The second part is the isomorphic as rooted trees part, and that says that the corresponding levels of these vertices are the same. So for example, we could look at a tree that looks like this. So here's our rooted tree, T1, and then we'll look at another rooted tree. And that's our rooted tree T2. Are they isomorphic? As graphs, they are certainly isomorphic, but also as rooted trees. So why is that? Well, we can get this isomorphism F from one to the other, such that all the edges are preserved, but also the levels of the vertices are as well. This vertex, which is the root, gets mapped to that root. This child gets mapped to that child, and so on. This could be our mapping, F, that takes all of these vertices in this way. And what we see is that if we map all of these vertices in this way, that no matter what vertex I consider, let's say this one here, it's at level 1. The corresponding vertex it gets mapped to, also at level 1. This vertex is at level 2. It gets mapped to a vertex also at level 2. So that's this second part about them being isomorphic as rooted trees. And this is as opposed to something like this, where I've got this tree, T3, and T3 is isomorphic to T1 and T2 as graphs. So for example, this vertex and that vertex, they correspond to each other. This one and this one up here, they correspond to each other. And then similarly for the sort of these subtrees, they correspond to each other as well. So we can see that as graphs, those trees are isomorphic. But as rooted trees, they are not isomorphic because this vertex is at level 0, whereas the corresponding vertex in this graph is at level 1. So the levels of the vertices aren't preserved. So what we have is that T1 and T2 are isomorphic as rooted trees, but they are not isomorphic to T3 as rooted trees. T3 has height 1, 2, 3. So I got the height by just 1, 2, 3. The length of the longest path down it. But T1 and T2 have height 2. If they were isomorphic as rooted trees, they would also have to have the same height, because the isomorphism of a rooted tree means that all vertices at a particular level get mapped to all vertices at the same level. And similarly, these 3 vertices are getting mapped to these 3 vertices, which are at the same level. So the heights have to be the same. So even though T1, T2, and T3 are isomorphic as graphs, they are not isomorphic as rooted trees. So we might as well put that one in here. T1, T2, and T3 are isomorphic as graphs. And now we'll just introduce one last bit of terminology. And this is what an m-ary rooted tree is. So an m-ary rooted tree is one for which every internal node or vertex has at most m children. So every internal node has at most m children coming off of it. In the case where m is 2, a 2-ary tree is also referred to as just a binary tree. So that's where every internal node has at most 2 children coming off it. So let's find all binary trees of height 0, 1, and 2 up to isomorphism. So we'll list them by their height. And so this will be height 0. And we will draw the tree in here. So at height 0, again, we are searching for binary trees here. What could it look like? Well, height 0 means that it's just the root. There are no children off of it. So that's it for height 0. How about height 1? So we've got our root. It's a binary tree. So it's got to have height 1, so there has to be a child. Because it's binary, you can have either one child or we could have 2 children. And that's it for height 1. So now we'll go ahead and do the height 2s. So we've got our root. It's got to have height 2, so there's got to be a child off of this one, and then that one also has to child. So this root has to be a grandparent. So what can we have? Well, it could be one child and then one child. Or from this root, we could have one child and then 2 children. So that exhausts all the cases where the root has one child. What about if the root has 2 children? So it could look like that, but it's got to be height 2, so one of these vertices have to have a child off of it. So we could have one child off it. Notice we're only interested in up to isomorphism. So I don't need to worry about the case where I put that edge over here instead, because that's just isomorphic. So what else could we have? Again, we're in the case where we've we've got 2 children. Well, they both could have 1 child. Something like that. Or, again, we've got 2 children. We could have one of them has 2 children and the other one has none. Or one of them has 2 children and the other one has 1. Or each of them has 2 children. And we've basically exhausted all the possibilities at this point. So how many did we get? 1, 2, 3, 4, 5, 6, 7. So we've got 7 binary trees of height exactly 2. Now we're going to be interested in counting these things. So the next question says, let Bn denote the number of binary trees of height at most n. Find B0, B1, and B2. So let's go ahead and find B0. Number of trees of height at most 0. While referring to our listing above, the number of trees at height at most 0 is 1. How many binary trees are there of height at most 1? Well, there's all the ones of height at most 0, plus the ones that have height exactly 1, which from above we found 2 of those. And so there's 3 in total. So again, if we want to think in terms of sort of our diagram above, B0, all the trees of height at most 0. It's just that one. B1, all the trees of height at most 1, which includes the ones of height 0 plus the ones of height 1. B2 is going to be all the trees of height at most 2. But we've already counted these ones. We've already counted these ones here. That's B1. So if I just take B1 and add to it the number of trees I found at height 2, then I will get my answer. So this was B1 plus 7, or in other words, 10. So there's 10 in total. Height at most 2, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. Now what we want to do is we want to use the recursive structure of rooted trees to find a recurrence for Bn. So we're going to find a recurrence for the number of binary trees of height at most n. The thing to note here is that for a binary tree of height at most n, removing the root, we get at most 2 trees of smaller height. So just to indicate what we mean by this, if we go back to our diagrams above, if I look at my trees of height at most 2, so if I look at some of these at 2, if I remove the root, then what I get is one of my earlier trees. Or if I remove the root here, I get a couple of my earlier trees. And so that's all we're saying, is that if we remove the root, then what we get is some trees we've encountered earlier in our list. So that's our big observation, and that's the recursive nature of how we're going to solve this problem. So this gives us a way to solve the problem recursively. So what are the cases that we have? Again, we're trying to find, so the key fact here, one that we have to pay very close attention to, is Bn is the number of binary trees of height at most n. At most n. Not exactly n, but of height at most n. So what are the cases then that we're going to consider? Well, our root can have 0 children. It could just look like that. Our root can have 1 child. So it could look like this. Or our root can have 2 children. So it looks like this. And now in each of these cases, we need to figure out how many possible trees there are. Well, in the case our root has no children, there's just that one tree. It's the isolated vertex. But what if there's one child? Well then, what's hanging off that one child is now a tree of height at most n minus 1. And if our root has 2 children, then what we have hanging off of those 2 children are trees of height at most n minus 1. So then we just think of how many ways there are to populate these places for trees. So how many binary trees are there of height at most n? Well, there's going to be always this one, that isolated vertex, plus the number of trees that are going to come from this picture here, the root having one child. So how many of those are there? Well, it's the number of ways we could fill this position with a tree of height at most n minus 1. There are how many choices for a tree of height at most n minus 1? Well, there are at most b sub n minus 1 trees of height at most n minus 1. So any one of those I could pick to fill this spot. So there are b sub n minus 1 choices to fill this spot. So we have b n minus 1 plus, and then how about the filling these 2 slots? So what can we do? Well, we could either fill them with different trees. So there are b sub n minus 1 possible trees that I could put in each of those slots. If I want them to be different, then I just choose 2 of them. So b sub n minus 1, choose 2 ways to fill spots with different trees. Or I could put the same tree in each spot. In that case, I just pick a tree from the b sub n minus 1 possibilities. I pick one of them, so that's b sub n minus 1, or b sub n minus 1, choose one, which is just b sub n minus 1. Ways to fill spots with the same tree. And so what we have is that this is plus b sub n minus 1, choose 2, plus b sub n minus 1. Or in other words, b sub n is equal to 1 plus 2 b sub n minus 1 plus b sub n minus 1, choose 2. And that's for n greater than or equal to 1. And so there is our recurrence relation for the number of binary trees of height at most n. And of course, we've got to add our initial condition in. So, and b sub 0 is equal to 1. So there's our recurrence relation with our initial condition. Let's see how we've done. We've worked out a few of these terms already. Let's make sure our recurrence relation is giving that to us. So b0 is 1. That's our initial condition. What about b1? b1 is 1 plus 2b0 plus b0 choose 2. Or that's 1 plus 2 times 1 plus 1 choose 2. 1 choose 2, that's 0. 1 plus 2, that's 3. And that matches what we had above. So we match that value. Now let's go ahead and work out the next value. What about b2? That's 1 plus 2 b1 plus b1 choose 2, which is equal to 1 plus 2 times 3 plus 3 choose 2. Or in other words, 1 plus 6 plus 3, or 10. And that matches the value we found out there by actually listing them. So we're pretty confident at this point that we've come up with our recurrence relation to count the number of binary trees of height at most n. All right, so that's it for this section. Thanks very much for watching, and we'll see you again next time.